Hi, Q12. Here is question 12 from exercise 8b. I did some answers for this and I put them on Wednesday the 6th of May box. So if you need any work solutions for any of 8b, that's where they all are. Alright, so what this question is asking is, a quadratic model can be used to relate the distance of the visible horizon, d in kilometres, at sea to the height of an observer's eye above sea level, h in metres. It is known that the horizon is 9 kilometres away when the observer's eye is 5.4 metres above sea level. Now this one was a little bit tricky, so I thought I'd go over it with you. So just a couple of things you need to know. Obviously the capital D is distance of the visible horizon, and h is the height of the observer's eye above sea level. Now, in the last sentence of the question, it is known that the horizon is 9 kilometres away when the observer's eye is 5.4 metres above sea level. This is something called direct variation. That's what it's called. Okay, so this is implanted throughout all these topics. We used to do this as a standalone topic, but now it's implanted. So this is what direct variation basically is. So what you're doing is you're given some information in the last part of the question and you have to substitute that into the equation. Now A says if the equation to model this situation is of the form h equals 1 over p d squared, where p is a constant, use the known information to find the value of p. Alright, so what you have to do is you have to use the d equals 9 kilometres and the h equals 5.4 metres. And you have to substitute that into that sweet formula they've just given you. Now in algebra, you have to remember that this can also, can also mean this, which also means, see how my d squared is on top there? It's in the numerator. It's the same as being over 1. So that means the 1 times the d in the top. So the 1 times the d squared on the top becomes d squared up in the numerator. And the p times the 1 on the bottom just becomes p in the denominator. Okay? So be aware it can also be written like this, and that might make a bit more sense to you. Alright, so now I'm going to substitute d for 9, or 9 for d, and 5.4 for h. So when I do that, I should get something like this. And when I solve that, the first thing I do is 9 squared turns in 81. And I say, okay, 81 divided by p. I'm going to get rid of the p first. So I multiplied both sides by p first. Cross out the p's. And I end up with this. 5.4p equals 81. I need to get the p on its own. So I divide both sides by 5.4 to get rid of the p. Cross off the 5.4s as you see. And you should end up with, on your calculator, 81 divided by 5.4 gives me p equals 15. Beautiful. So once I've got that, I now substitute the 15 into the place of the p, and you'll have a new equation. So either you can use the original equation, h equals 1 over 15 d squared, or h equals d squared over 15. So that's the first part of B. Now the second part of B says to draw the graph. Alright, so what I did instead was I used graphic technology. There it is there. So I put that in. So remember, the h is on the left-hand side of the equals, so that's like a y if you're using Desmos or anything else. And the d is the independent, so that's actually the same as the x, okay? Alright, so that's how you put it in, and that's what it looks like. Now it said for values of d up to 15 kilometres. Now the d is where the x goes, so the kilometres is along the x-axis. And the meters, or the observer's level above sea level, is on the y-axis. So the first one, C, says use the graph to find the height of a person's eye above sea level for the distance to the horizon to be 7 k's. Distance is x, so 7 k's is about here. And I'm going to move, just past it. So there, it's about 3.2. All right, it was about 3.2 if you got that really quickly. And then D says use the graph to find how far a person can see at a height of 10 metres. Now 10 metres is the y. So go up the y-axis to 10 and go across until you hit, okay, all right, and the second number should be a 10. not so good with my finger. So it's about 12.26, maybe a little bit less. No, can't quite get there, okay? But it's somewhere around there, between 12.24 and 12.26, so let's assume it's 12.25. Okay, now then it says confirm your answers for C and D by substituting into the quadratic. Now this is always a good thing to do, to double check your answers in a test. So down here, okay, here is question E. So for part C, D equals 7, so I'm going to put 7 where the D goes, and that gets me to do 7 squared divided by 15. That gives me a more exact answer of 3.3. Okay, just because obviously in a graph, in a test, you can't be that accurate. And for part D, now I'm going to put 10 where the H goes, so I end up with 10 equals D squared over 15. Get rid of the 15s first, multiply both sides by 15 first, cross off the 15 with the D squared here and here. Okay, and then you get 150 equals D squared. Do the opposite of squaring, which is square root. That's why I've got a square root symbol around the 150. And I write my answer as D equals the square root of 150, which ended up being approximately 12.2, which is what you also read. And it was 12.24 something, which would have been close to 12.25. Okay, there you go. There's question 12. See ya.